Hello, everyone. My name is Randy Stott. I'm the managing editor of Gear Technology and Power Transmission Engineering magazines. I'd like to welcome all of you to this afternoon's session of Ask the Expert Live. Today, we're going to focus on the topic of cutting tools, and I've got some gentlemen up here who are ready to answer all of your questions. So please remember, this is an audience participation event. We would love to have you asking questions, and we'll get you the answers. Before we get started, though, I'm going to have each of these gentlemen introduce himself. Please, John, if you would begin.
Okay. Hi, I'm John O'Neill, engineering manager with Star SU for gear cutting tools. I've been either manufacturing or designing or applying gear tools for about 35 years.
My name is Nicholas Byron. I work as engineering manager in Schaumburg, outside of Chicago, for Sandvik. And we have there designing, quotation, testing, and application support of gear tools for the Americas.
Herman Stadfeld. I'm Vice President of Research and Development and Bevel Gear Technology at the Gleason Corporation. My experience goes back also, maybe not exactly 35 years, but that explains that I'm younger than he is. No, but it goes about back 30 years. When I made my PhD at the Aachen University in 87, that was already about bevel gear geometry, bevel gear processing. And then I worked first at Oerlikon in Switzerland, and after that at the Gleason Corporation about since 1994 in that position.
Thank you, gentlemen. Before I begin with questions from our readers and the internet, does anybody from the audience have a question to start us off? All righty. First question is, when are short lead hobs needed and how do you select them?
Typically, if there's a problem with natural undercut or undercut from a protuberance that works its way up into the active profile of the gear, we'll short lead the tool to move the undercut lower on the profile.
I would like to add that it usually has a beneficial effect on tool life, since the wear on the tools of the hub gets more evened out. So we see a considerably longer tool life of the hub in short lead hubbing.
Regarding the tool life, when we use short lead hubs, we have lower pressure angle and low back-off angle. So how does it affect the tool life?
Well, you have to use a higher cam angle with the smaller pressure angle. So usually you get a shorter tooth length, usable tooth length. But as Nicholas said, you may improve the number of pieces that you get per grind. So it tends to balance out a little bit.
Thank you, gentlemen. On a related question, do hobs and shaper cutters need to be recoated after use?
Well, we'd prefer you don't, then we'll sell more hobs and shaper cutters. But typically, if you want to maintain the same performance you had with a new tool, you would recoat after sharpening.
You grind them, when you resharpen them, the principle is that you grind them on the most vulnerable surface, which is the front face, where the chips roll off, where you have the most heat, chemical contact, and so on. And so if you don't recoat them, you will have one very good tool life and one certain, during development, part properties, surface finish properties, and you won't find them after you resharpened it. So you should recoat them. And there you have the problem maybe sometimes because you strip the hob. Because if you just coat on top of coating, you get some geometrical problems and also some flaking danger. So you strip the hob, and depending on what material you use, high-speed steel carbide or what, you can only strip a hob chemically a certain number of times.
Thank you, gentlemen. Next question is from a reader. When does it make sense to use gashing, and when does it make sense to use hobbing?
Well, that's a pretty complex question. If it just depending on productivity, when you have a low number of teeth, a gasher is going to be faster than a hub, because the tooth gap is getting very wide and a small pinion, you have very few active spirals on the hub, but the gash will be in the whole gap. So that's very efficient. And you have a few indexes when you have less teeth. So that's kind of the first consideration. Pinions generally better to gash. On the other hand, you have a disadvantage that a certain DP on a disc only works for a certain number of teeth, because the changes, a hub, a DP2 hub, for example, would work for 15 teeth to 40 teeth. So it's a pretty complex question. Something that can be good is to use both. To have a gasher with standard insert, just a V-shape, 20-degree pressure angle. For example, roughing out the gaps, shift over and use a hub, an inserted hub, or maybe even better, a high-speed steel hub, ground to form, a high-precision hub to do the finishing. We often see that the investment needed for a hub is you need to do a lot of parts. So the first step could be to go to a gasher instead of an inserted hub. So.
However, where you always gash, there's internal parts. You have to gash them.
Yeah, of course. Yeah.
Yeah, you may use a gasher if you have very difficult to machine material. Take the material out with a gasher and then just use a high-speed steel hub to finish the part. As opposed to trying to hob that material out, you would need a solid carbide hob in some cases.
Yeah, and you can do a double gasher. You get half the number of shifts and a really lot of productivity.
Very good. Thank you, gentlemen. I'm going to switch topics now, and I'm going to ask about bevel gear cutters. And if we could just go over what are the different types of bevel gear cutters?
Yeah, I think you have the face cutter system. Face cutter system, you have a disc where the blades stick out the front, and a number of blades represent one tooth of a generating gear. So that could be in a continuous process called face hobbing, or in a single index process, face milling, but the cutter blade as it moves always represents a tooth of the generating gear. Now the face milling cutters, it's a face cutter with all blades behind each other on a circle in a row. So you have outside blades, they describe from one to the next a circle, and the inside blades as well. With the face hobbing cutters, you look at groups of blades, and an IB blade and an OB blade, they are oriented in a shape of a spiral. Although, of course, they describe a circle as well, but they're in a spiral, and they cut one slot. In the process, the next two blades would cut the next slot, where for the face milling process, all the blades cutting first one slot, and then you index to the next slot. Now we have different variations of other cutters for bevel gears. Like, for example, for straight bevel gears, we use peripheral cutters. Those are discs where the blade's sticking out of the side, so at the periphery. And those cutters are made with a pretty large diameter, such that when you have a relatively small face width, or some face width, that when you cut from the top in the slot, and the cutter actually represents one side of the generating rack. It's like in cylindrical. In straight bevel, they're easy to understand. They're like cylindrical, only that the rack is not parallel, but it points with every line to the crossing point of the two bevel gear axes. But other than that, it's a rack. And now the cutter, actually one side of the cutter describes this plane, so it's under this angle that the pressure angle is, like it's 20 degrees, the cutter is tilted 20 degrees, and then it would cut in and roll out one slot. So that's the system for straight bevel gears. Then there's a system for face gears that is similar. The face gear cutter is a peripheral cutter that has blades sticking out of the periphery of the cutter. The blades are not straight, like straight lines, because they're not representing a part of the generating rack, of a flat, plain generating rack, but they actually represent a tooth of the involute mating pinion member of a face gear. So the blades have to be crowned like an involute, yet at the calculation point, so at the pitch point, they are tangent to the 20 degrees, for example, that the face gear has a pressure angle. And are there other bevel gear cutters? I think old-fashioned bevel gear cutters, where blades were bolted on the side. I've talked now more about stick blade cutters. They have a stick that might be that long, and the stick is topped down from the top, recrowned, and then exchanged. Actually, that cutter system is very powerful compared to older bevel gear cutter systems, but also compared to cylindrical gear hobbing or cutting, because if a blade breaks or if some chipping happens, etc., you top down that blade a little bit more, you exchange it against another stick, and you're back in business. If you had a solid carbide hob and one or two blades break out, you basically throw away the hob. So it's a very universal system. Also, this system versus very older bevel gear systems where the blades were bolted on, you would purchase the blade from the manufacturer, in our case Gleason, and the blade has a certain pressure angle, and it might have a curved blade with a little curve on it, a tip edge radius, and all this is defined. Now you make another job that requires a different tip edge radius and maybe a 2-degree different pressure angle. You're gonna buy different blades. And 3 months later or so, you're back in business. With a stick blade system, you make that same decision, and the same afternoon, you're cutting your first prototype.
Yeah, and also that's coming a bit for lower volume when 5-axis machining of bevel gears, straight bevel gears and spiral bevel gears. And there is many producer of machines here that are working on it. It's still a bit immature, I would say, but there is possibility to do that. And the cutters in that case are capped, and it's a series of cutters. You would start with a standard off-the-shelf cutter, and then the deeper you go, the more custom, more like a parabola or a capped form cutter. So that's something that's coming for prototyping and lower, smaller batches.
Thank you, gentlemen.
I have to say something after him, right? Because of the 5-axis machining. Actually, who is interested to do with Universal Tools? We just shipped our first machines with a process that we call Unimill. You put either a tapered end mill or a dip disc cutter or a cup disc cutter. You put on the machine and you tell the machine which cutter that is. What is the beauty of it? You do it on a bevel machine. It has all the stiffness and the accuracy of a bevel machine, and you treat it like a bevel machine. You actually see the radial distance, although the job doesn't have a radial distance. You see, and you can influence it. You can make a GH corrections. You go for measurement, and the bevel gear GH calculates the correction, feeds it back, and it understands that. So this is for, let's say, not for big gears then, but that is for prototyping. If somebody needs 5 gears, but also is the beauty of this Unimill, which really works with an off-the-shelf end mill, for example, is that the process actually emulates the face cutter process. That mill it doesn't use a grid of surface points and normals. It uses the basic settings and knows the path that a blade in a face cutter would do. And now this cutter leans on the one side tangent where the blade would be and follows that path, but only where the face width is, and then it turns around and goes to the other flank. So saves a lot of time, but the thing is, the 5-axis machining manufacturer, they explain you that if you had a pinion with undercut, you could make it on a 5-axis machine without undercut. But why does a gear have undercut? That the opposite tooth of the opposite member gets through there, and you would have immediately an interference if you tried to put some cosmetics in the root. You need a different design for avoiding undercut, maybe a higher number of teeth or something, or a dendo modification, but not take away. Another thing for prototypes, the 5-axis machining, you have about 7 surfaces that you put a flank together. You have the 2 flank surfaces, possibly protuberance or undercut area, root fillet radius, and a bottom flat section. And you put them together. So your tooth, the generating flats on the flank and all, they have nothing to do with the original bevel gear. If there was an original bevel gear, like you make one for a marine application or for an aircraft application, you would not get this gear qualified because it has different texture. People making at the moment investigation if even the surface resistance is about the same. Now if you do that with this Unimill process that follows the bevel gear tracks, you see the identical generating flats that the original bevel gear would have or is going to have. You see the same undercut, the same root fillet. So you make your 5 prototypes, like for an automotive OEM, you go to that OEM and and have them for testing, those gear sets. They find the tests are good, and now you're at the time, because you got the business granted, to start production, and now you order the real cutter heads, the expensive cutter heads for mass production. But to get 5 prototypes done, if you had the idea today, tomorrow afternoon we could have those 5 prototypes in front of us, and they'd be authentic to the original Bevel gears.
Yeah, that sounds very interesting. Just want to add one thing. There is also the possibility to use sticks and have inserts on the sticks and change insert instead of regrinding sticks, which could have some advantages, since you can have better coatings and better carbide if you don't have the need to strip and recoat. So for roughing purposes, it can have its advantages. It's not going to be as precise as a ground stick, but for roughing it can have some merits.
We actually even promote the sticks for the finished product. And on the Gleason-Heller Machining Center, 5-axis Machining Center, at the Gear Solutions Forum, you could see a cutter that we call Slimline. It's like he says, it's a stick blade cutter, but it's nicely true to a high radial and axial accuracy, and we use it actually also for finishing.
Very good, thank you. Do I have any questions from the audience?
What about grinding into solid instead of cutting for prototyping?
Absolutely. If I had a grinding machine and I was to make prototypes and I had the opportunity to use Unimill or use grinding from solid, if I had a grinding machine available that maybe is equipped, with a fire extinguisher and all that you need for grinding from solid, or I could equip it with that, I prefer that, yes.
Thank you. Okay, this next question comes from one of our readers, and it's actually a 2-part question. Are multi-thread hobs worth the investment, and are there any side effects from using them?
Yeah, they're definitely worth the investment. In most cases, depending on who's supplying the tool, there isn't an upcharge until you reach a fairly high number of threads. So the investment in the hob itself is the same as if you used a single thread. Cycle time, tool life, higher numbers of teeth in the gear, the cycle time will definitely be impacted by the use of a multiple thread hob, significantly reduced through the table speed of the machine. In those cases with high numbers of teeth, you probably don't have a heavy enough chip load either, so the multiple thread hob allows you to carry a chip load that provides a good tool life on the tool. Some of the drawbacks of multiple threads, though, if you don't take good care in mounting the tool, you'll induce thread spacing error into the tool, and you'll see that spacing error in the part itself. You can also induce that type of error in the sharpening if it's not properly sharpened.
Yeah, and it can be some dangers to have a even number of starts and an even number of tooths in the gear. You can get more spacing error. As grinding is getting better of the hobs, that's getting less of a problem. But there's things like that comes from multi-start hobbing.
Yeah, usually the quality level of the hobs, I think, is there now, where it's not an issue with the hob itself. It's usually the care and the mounting of the hob that becomes the problem.
Thank you. Any questions from the audience?
I'd like to go back to the coding issues of hobs, and it would seem to me on some of the remarks that you made that there should actually be no reason why an individual customer should be sharpening his own hobs. It would seem to me today everybody should be sending the hobs back to the manufacturer to be resharpened and then recoated, stripped and then recoated. Is there any reasons why customers today continue to sharpen their own hobs?
Well, when you ask them how much it costs to resharpen, sometimes they don't calculate the cost because they think it's for free. Even we sell inserted hobs, we need to know what the burden rate is. We're in competition with solid hub sometimes, and it feels like many manufacturers don't see that cost, which is a cost, to have someone regrinding and maintaining the machine and all that. But I think it's a lack of understanding that it's not for free.
Give him the microphone.
Many manufacturers consider the grinding time for a hob to be in the overhead, so it doesn't show up against the job. Where if he sends the hob to you to be sharpened, it shows up as a chart.
Right. But it's still a cost somewhere.
Yeah, of course, if the tool life is improved through sending it back for resharpening and recoding to the original equipment manufacturer, offsets the cost savings that they believe they're realizing.
However, there are also manufacturers that resharpen their hobs and send them to local coating facilities. Coating has become so readily available, and they do the stripping operation also for you. So there is this combination: send them to the original manufacturer and have them sharpened and recoated, or go local, resharpen it yourself. I think any combination, as long as the quality is fine and as long, as they can calculate it properly, will work. But it's always recommended to, as soon as a front face sharpening is done and the coating is removed, is always recommended to recoat it somehow. It is.
If you sharpen the hob yourself, you can sharpen it, like the next hour. If you send it back, you're talking weeks or days.
Which brings us to the small batch manufacturer. For them, it's always justified to run the machine a little slower and be in business the same afternoon and finish that batch. I agree with that.
Along the same lines, have there been any advances recently in the coatings themselves that people should be aware of?
Yep, Balzers has just introduced a new coating at EMO 2 weeks ago, I believe. It's a it's a step forward from the current Alcrona coatings. Typically be used to run significantly higher speeds with the same type of tool. For example, you run 300 meters a minute instead of 200 meters a minute with a high-speed steel tool, as opposed to advancing to carbide for the same application.
Yeah, and in inserted tooling, there is coming out new coatings all the time from Sandvik and our competitors. Lately, Sandvik has come out with a coating that the crystals are orientated this way up from the face. That increases the tool life and the ability to go faster. So we don't need to be able to strip. The Alcrona Pro is a good coating, and it's good also because it's easy to strip. With inserted tools, you don't need to have the ability. So, yeah.
We actually run one cutting machine, day in, day out, only on single plate group cutting trials to test out new coatings. It's very difficult. Sometimes something was reported, works so nice for cylindrical gears, and it doesn't really have a merit for bevel gears. It's very difficult, and actually it requires systematic research to find out. And actually, the users of our system always can have this list, what the results were, which carbides we would recommend, approve, or whatever, and which coatings we recommend or approve.
Yeah, is an advantage. We talked a little bit about gashing before, for gashing out materials. If you have the ability to get also not just a special coating, but also a chip former on the insert on the face, which could improve tool life and productivity too.
Thank you, gentlemen. From the audience? Okay, the next one's from a reader. When is climb hobbing advisable?
Climb hobbing, typically if there's an interference point above the tool or above the part where you couldn't approach from the top, or you don't want to use a radial infeed at the top, usually you'll get a smaller burr from climb hobbing. Used to be a common thought that the tool life was better in certain applications. I think that's probably very difficult to prove these days with the advanced coatings and the materials of the hobs. So that's about it.
Well, the case of inserted hubbing, usually climb is better because the carbide likes a heavy chip first going out to a thin chip. Generally, it's better to climb for the tool life.
I think when you have a combination of roughing and finishing, you always advise to make conventional during the roughing and make climb for finishing. His chair fell apart.
Well, I think we see usually that we want to rough in climb, in hubbing, and it's from case to case. It's hard to sit here and say it's always going to be like this or like that, but we would start with climb, and when you climb, you also drag the finished chip, the cut chip, through the rest of the made tooth gap because you've already cut, so you can get surface problem. Are you always going to get that? No. Do you always know if it's coming or not? No. But you can go climbing first, look at the surface, and sometimes we go to conventional.
There's also another rule that's not only applying for bevel gears. If you climb, you need an infinite stiff machine when you climb in roughing, where when you rough with conventional, a standard machine will do, and it finishes with high surface finish in climbing. So it probably depends on the machine tool that you use and on the process, and obviously on the module of the gear.
Yeah, you probably want to avoid climb hobbing if you're machining something that's very hard. You want to start with a thinner chip instead of a thick chip.
Very good, thank you. Next question from a reader. What is the difference between a shaping cutter and a power skiving cutter?
There is none. If you had a shaping cutter for a helical gear for 20 degrees, you could use it as a power skiving cutter for a spur gear with a 20-degree axis inclination. So basically that's how power skiving cutter have been invented or developed. So they look, you couldn't at first view tell that's a power skiving cutter or that's a shaper cutter. But you see, the power skiving cutter always has the serrations for the helix, even though you cut a spur gear.
You might see some higher clearance angles if you looked at the design, but
Yeah.
from looking at the physical
that's
cutter
correct.
itself, you wouldn't see much of a difference.
Well, there is an advantage in power skiving to use carbide rather than high-speed steel because you can get a much higher cutting speed, an even cutting speed. In shaping, you have an uneven cutting speed. It's harder to use carbide in a good way. High-speed steel behaves very good in shaping, while carbide is less good. And power skiving is a little bit of the opposite.
That brings us to the second half of the answer, that in case that you use like a stick plate cutter or something for power skiving, of course that looks quite different than a shaper cutter. It's a stick plate cutter. In the case of our system, it skips several teeth because the blades go like raised to the center, and so you cannot get them close enough. So you skip, for example, slots, but you use carbide stick plates. They are coated, and yes, the advantages of carbide in power skiving, I can just confirm that. And I think Dr. Miller does similar things and also can confirm that this enters a new world of opportunities in power skiving, using coated carbide blades with three-phase grinding.
Yeah,
Or inserts that are three-phase refurbished.
Yeah, typically a scudding cutter you could make in a solid carbide, again, to get the type of speed you get out of the insert tools.
Do I have any questions from the audience?
I just want to refer to the carbide stick plate principle for power skiving. It's right that we get a much better tool life and we enter a new world in productivity. But on the other side, it only works if the customer has a blade grinding machine, a cutter setup machine, and all these extra fancy things that are usually only available in the bevel gear world and not in cylindrical gears.
Or has this telephone number. that he can call, can I send my cutter to you, my blades to you for refurb? It's done often today, and you probably do that also, but you're absolutely right. They're not independent, they need an external refurbisher, yes.
Okay, I've got one more from the readers, and that is, how does hob or cutter material affect feed and speed selection?
Well, typically, the more alloys in the hob material, the faster you're going to run. You go from high-speed steel to carbide, significantly higher speed. In some cases, though, you do have to reduce the feed rate as the hob material is advanced.
Maybe a reflection on that one is that at really small modules, the difference between high-speed steel and carbide is not that big because there's not so much material to take out, not so much heat. But as the module grows, the advantage of carbide is getting bigger. And a way that goes back also to the gashing we talked about earlier. At big modules, you can really save on the high-speed steel hub by roughing out a lot before. At really big part can make you be able to do the whole part and not needing to change in the middle. So the bigger the gear, the more getting out, the more important it has.
Maybe interesting to round this off for the bevel aspect, that where people in cylindrical cutting have a lot of success with those super high-speed steels, with a lot of alloys in it where you can cut faster, you can even consider tri-cutting. It seems not to be successful in bevel cutting. We do that also with our single blade groups. If a new material comes out or a material improvement was done, we use coated stick blades that are from a high-speed steel, some kind of an ASP or sintered high-speed steel material. And at the end of the day, we find out it can not even closely compete to carbide stick blades. So we have not been successful over many years trying. And that started with the time with you, David, when we made the first comparisons.
Of course, every time a new coating comes out, that changes that equation again, where you may drop back from carbide to a higher level high-speed steel.
I don't believe that a new coating will change the situation in between HSS and carbide in the bevel gear. The situation is completely different because we have a very long line of contact for bevel gears in between the cutting edge and the flank, whereas in cylindrical gears we just have these little comma chips and not these long ones. So we have a very high thermal impact on the cutting material itself, and this is not good for HSS. Independent from the coating, and I don't believe that the coating has such a big thermal resistance that the core will not get warm. That's hard, at least for me, to believe it.
Yeah, typically those new coatings do have more thermal resistance, but it may not be enough.
I mean that's something that we dream of. That and I dreamed of a long time. That the material, the substrate on the base, gives you just the hardness and the support, and then the coating takes care of the heat, the chemical resistance to the base material. However, what Dr. Müller says is actually a good explanation for many of the problems that we have. The carbide is chemically and from its binding is destroying itself, or is being destructed and destroyed underneath the coating. The coating is still good and the carbide is already bad. That happens actually due to that long contact and the heat that goes still through the coating underneath into the carbide.
Yeah.
Thank you, gentlemen. Do I have any other questions from the audience?
If you're finished, I have a question for you.
Go ahead, Doctor.
This is a specific question. About 45 years ago, somebody told me the customer isn't always right, but he's always the customer. So I have a client who wants a gear design. Number one, he wants it to be a 20-degree pressure angle, and he wants the pinion to have 5 teeth. So he's now tied both hands behind me. So I designed this unit with as high a profile shift as I could to avoid a pointed tooth. So I have almost a 0.5 profile shift, and I've got an undercut that when I'm finished gives me a 0.8 contact ratio. I can't hob the gear, it's not gonna work. Can I short pitch hob it? Do you know? Or do I need to find another way to cut the teeth?
You should be able to short pitch hob it, but with that small number of teeth, it may not do any good because the tip of the hob tooth gets wider and you end up with the same undercut.
Have you considered gashing it instead?
Well, that's the next option. Is can gashing be used, or do I need to use a 5-axis milling machine?
Well, I think we should look at how the shape looks, but if you don't need an undercut, you can go straight down after the profile. You can use a disc cutter, most likely.
Could use an involute shape end mill also.
Fortunately, it is a spur gear, so that might help.
One more question from the.
It's not a question, it's just, you mentioned the customer is always right, and I fully agree. Unfortunately, mathematicians are also always right. And one of the problem is, undercut is not something that is just because of hobbing. Undercut is something that is needed because of the number of teeth. And even if you would use an involute profile end mill or something like this, you only have the pinion, but it will never be able to mesh with the gear, because you need this undercut area for the tip of the mating gear so that it moves. It's unfortunately, customer is right, but mathematics is mathematics. I can't change it.
Brings us back to the beginning, right? When I said in 5-axis, why would you tried to get rid of the undercut and make a nice, beautiful root fillet, but it ain't gonna run with its mating member.
But if it's only 5 teeth, you can probably make an undercut with a gasher by turning it and get access to make that undercut. Maybe with another disc, having 2 different discs. A involute shaped disc for the profile and then a standard disc for making undercuts.
The formula for the minimum number of teeth to avoid undercut is 1 over the square of the sine of the pressure angle. The only thing you can change is the pressure angle. Then you have a little better condition for undercut, but that's all.
Thank you, gentlemen. Do I have any other questions for the experts?
Maybe 10 more years ago, there was an article in Gear Technology magazine about advantages of reverse hubbing by some Japanese company, meaning opposite hub lead direction to the lead of the gear. Yeah. What's your opinion about this? Is it really is there any advantages of this?
I'm not a cylindrical expert, but I'm teaching a class on gearing, and it starts with cylindrical and with the generating principle. And actually, you would already from the drawing, you would always advise stay away from that. The distortions that you get, every hub would have certain distortions because of the kinematics and because of the fact that it's not like a cam that goes up and down and has a perfect trapezoid, but it is a worm that winds around the body. So now if you make the reverse spiral direction, all the distortions that you have to expect, they really be magnified. Not only a little bit by a % or 2, they really be magnified. That's my opinion. But you could use it for small quantities if you have want to save a hop.
Stay away from it.
I would stay away from that if it's possible.
Anybody else with a question? All right, at this time, I'd like to thank you all for coming to join us for Ask the Expert Live. I'd most especially like to thank our 3 experts today, and if you could help me in giving them a nice round of applause.
Ladies and gentlemen, thank you for participating in Ask the Expert Live. Our next session is tomorrow at 10:30. See you then. Until then, enjoy the show.